Good afternoon, everybody. Let's get started with the class. So for announcements, don't forget homework 4 is due this Friday. So take a look at that. That is posted on Canvas. You will start Lab 6 this week. Lab 6 is all about building sensors, putting sensors into your test bed. So I think this is going to be a fun hardware lab. So I wanted to, whenever I seem to get down into the weeds a little bit, I like to take us up to a bit higher level and show you where we are in the class and the topic. So this is our diagram of what we're talking about when it comes to power sources and control. So we talked about power sources, we talked about batteries, we talked about solar panels, we talked about battery capacity, estimating battery life. And then we just finished up talking about controlling power delivered to loads through either mechanical control like switches or electronic control like relays. And then we spent a bunch of time on MOSFETs because those are really used a lot in control of motors and solenoids and robotics, either alone or inside integrated circuits, integrated into circuits. And so we just started talking about converting voltages because you have a power source, maybe a battery that has a voltage that goes down over time as the battery discharges, and the rest of your circuit needs a constant voltage usually, or voltages, multiple voltages from one power source. So we're talking about now, we just started up last time, converting voltages using linear regulators and switching converters. So we're going to talk about both of these. We're going to get into different types of DC to DC converters, and we'll continue that discussion. Okay, so last time we left on this slide talking about DC voltage conversion, and I'm lumping two topics into DC voltage conversion. I'm talking about linear regulators, and I'm talking about switcher converters and regulators. Uh, the switcher type is what you're using in lab on that board you have in your project. And I mentioned that linear regulators use this pass element to cause a voltage drop between a source and a load. And that means the source voltage has to be higher than the required load voltage because there's a drop across the regulator. If you have a big difference in voltage between the source and the load, let's say the source is a battery, the load is some lower voltage. If you have a big voltage difference, you can get poor power efficiency, and I'm going to show you why in a minute. And I mentioned switcher converters and regulators. They use a pass element and an inductor and a capacitor to step voltage up or bring voltage down. We'll talk about two different types, those types. They generally have good power efficiency because they're using switching versus a voltage drop across an element. Okay, you saw that when we studied MOSFETs, if you operate a MOSFET in a circuit like with pulse width modulation, either in an on state or an off state, that you get good power efficiency because you don't simultaneously have a voltage and a current, much of it, through the element, through the MOSFET. But even though these are more efficient, these switcher converters, they're larger, they're a little more complicated, they can cost a little more, they take up more board space, so they add weight. So the answer, as always, is it depends what you need. All right, so let's focus in on linear regulators. So both of these are used, right? It's not like one is used 99% of the time and the other is used 1% of the time. They're both used, and it depends on your application. So let's start talking about linear voltage regulators. So these devices actually use a feedback loop to adjust the voltage drop of a pass element. Okay, so if you look at this schematic here, we have a source, and let's say that source is, some voltage like 6 volts, and then you have a load, and that load is a 5-volt load. So you want to convert or change 6 volts to 5 volts. So here's the voltage regulator in this blue box. This is the linear voltage regulator, and it has this pass element here. So that pass element is, well, it's a MOSFET here. And there's going to be some voltage drop. In this case, we're going to try to maintain a 1 volt drop to convert 6 volts to 5 volts. Okay. And then there's this feedback loop in here, this control loop. So what this control loop does is it tries to minimize the error between the load voltage, like the actual load voltage measured by the control loop, and the desired load voltage. Okay, so here's how this control loop works. You have this resistive divider here, that it's a voltage divider, and it drops down a voltage to a certain level, right? It might make up a number, divide by 5. So this might be 1 volt here. And then you have a reference voltage, which would be 1 volt. And so what this control loop is trying to do is make the input to this, essentially an op amp, the two inputs equal. So if you remember back to circuits class when we studied op amps, in this kind of control loop with negative feedback, the loop is going to drive the input differential voltage of the op amp to approximately 0. Okay, so it's going to try to make these the same, and that's how this control loop is working. So that sets this gate that is an output of the op amp to this gate driver, and the gate driver controls the voltage that is the input to this MOSFET. So this MOSFET can control this IX current, so it provides more current or less current, and that adjusts this output voltage here, right, using that control loop. Right, so that's how it works. So the if more current is required by the load, this control loop is going to adjust so IX increases and it maintains a constant output voltage here. Right, so kind of bringing the op amp topic into this from circuits class. Okay, so that's basically how this works, and V source needs to be higher than V load because you only have a voltage drop here. You cannot have a negative Vx here to increase the voltage. And since Vx is non-zero, right? So you have a non-zero Vx across that pass element, and you have a non-zero current. That's the current going to the load. Then you have a power loss. You have this power Ix times Vx dissipated by the pass element. Okay, so that's heat, right? This linear voltage regulator is going to get hot. It's going to use power and energy from the source that you don't really want to use to heat up the linear voltage regulator, but it happens. Okay, that's just a consequence of this architecture. So the power efficiency is low when the source voltage is significantly higher than the load voltage. Okay, because then P equals Ix, Vx is large. So if Vx is large, that means you have a big difference between the input and output voltage. Then you have a larger loss. Okay, but as an advantage, these linear voltage regulators are available in tiny integrated circuits. Okay, so in general, if you have a source voltage that's just a little bit higher than the load voltage, what's a little bit higher? It depends. There's different types of regulators with different what are called dropout voltages. That's the minimum voltage between the input and output. If you have just a small difference, then they can be efficient enough, and they're relatively low noise. They are low noise compared to a switcher converter. So if you have something like a radio receiver, an audio amplifier, a sensor circuit that's super sensitive, you can use a linear voltage regulator to help keep noise off the power supply line and to provide regulation. Okay, so these decoupling capacitors on the input and output, they're usually there to reduce noise on the power supply wires, lines, and they also provide stability. Some linear regulators require certain value capacitors to provide stability of this control loop. Right. So what if you have a voltage at the input, or I should say you have a voltage source that is much higher than the load voltage, and you still want to use a linear voltage regulator to have clean power, to have low noise power. Well, what you can actually do is use a linear regulator following a switching regulator, which we're going to talk about next, to achieve better efficiency because you can get the input voltage closer to the output voltage. And then you can actually use that linear voltage regulator to lower the noise from the input from the output of the switching regulator. Okay, so that's why I mean these approaches, switching regulators and linear voltage regulators, are both used, and oftentimes they're used together. So, all right, so that's the one approach that I wanted to talk about, this linear voltage regulator. Let's move on to switching. The switching approach, also called a DC to DC converter. So we're going to talk about a step-up converter. That means this increases the source voltage to a higher load voltage. Okay, so a switch mode boost converter. This is called a boost converter, a step-up converter, increases the voltage so you can have a higher load voltage compared to the source voltage. So here is the schematic of a basic boost converter. Okay, so on the left, we have a voltage source. And that voltage source could be a battery or some power supply. And it might even change over time. For example, if a battery starts going dead or starts losing its capacity, going down. And then you have a load voltage that you would like to maintain, and you want it to be constant. And that load voltage is higher than the source voltage. Okay, so we have an inductor. I have a switch here. The switch is in a closed position here. There's a diode and a capacitor. So in between these terminals, these 4 terminals here, that is the boost converter. That's the DC to DC converter, also known as a boost converter or step-up converter. Okay, that switch is really 1 or more transistors, like a MOSFET. So this isn't a physical switch. So when you see a switch in these diagrams, think MOSFET. It's an electronically controlled switch. That switch is going to open and close. And that action of opening and closing in this particular duty cycle is what causes the source voltage to be stepped up to the load voltage. Okay, so let's look at 2 cases, when the switch is closed and when the switch is open, how the current flows through this circuit, and how we actually get the voltage increase. Okay, so when the switch is closed, you have this. The switch connects the inductor to the source voltage directly. So if you look at the voltage across this inductor and you wrote a KVL equation, Kirchhoff's voltage law equation, you would see VL equals V source. So you have a DC source connected directly across an inductor. Okay, and so what happens is the inductor current increases as a ramp function, because remember, the inductor current is proportional to the integral of the inductor. The inductor current is proportional to the integral of the voltage across the inductor. Okay, so if you really write out the equation, there's a 1 over L here, and there could be an initial current. But I'm just showing that this is a ramp function. You get the inductor current rising as long as that switch is closed. Okay, and you generally don't want to connect an inductor to a DC source for very long, because what happens is that inductor current just keeps going up. It just keeps rising, and eventually something bad happens, like the inductor burns out because of the resistance in the wire, or the source hits its maximum current. You know, something undesirable happens usually when you just connect DC directly to an inductor. But in this case, we have the switch opening and closing, so we only have the DC voltage applied to the inductor for a short period of time. But nonetheless, we get this increase in current through that inductor. Okay, going to the right here, you see this diode. So the diode blocks any reverse current from going through that closed switch. So right, if you look at this, we have a capacitor that could be charged. And if you short, right, if you didn't have that diode, you'd be shorting across that capacitor. And so you think that, well, wait a minute, I'm going to discharge that capacitor through a short. That's not good. But that's what that diode is there for. That diode blocks the current from going right to left through that switch. All right. Okay, so but what's happening, let's look at this capacitor. So any charge stored in that capacitor actually provides current to the load. So let's say that capacitor, you've been running this circuit for a while. I'll show you how this works. But if that capacitor is charged, that capacitor is discharging its energy into the load. So it's providing current to that load. Let's say the load is a resistor. So now you have a resistor connected to a capacitor. You're going to get this RC time constant exponential discharge. So the voltage is going to fall across that capacitor. So V load is going to fall. Okay, but if you have a very large time constant, remember back to basic circuits, if you have a very large time constant and you're only supplying current for a short duration, then you only get a little voltage drop across the load. Okay, so that capacitor is what maintains the voltage across the load, at least for a short while, when this switch is closed and when that diode is blocking current from going to the left. Okay, so your load is powered by the energy stored in the capacitor. Okay, so that's when the switch is closed. That's what the current flow looks like. Let's look at what the current flow looks like when the switch then opens up. Okay, so you have this. Now you can see the current path, right? So you have current flowing from the source into the circuit. That switch is open, so current no longer flows down through that switch, and current can flow through that diode. But so the inductor, since on the left, when the switch was closed, it built up a magnetic field. And at this point, you have the inductor, the magnetic field induces a voltage that keeps the current flowing. Remember, an inductor tries to maintain the current through itself, right? And it's going to create a voltage that opposes any change of current, right? Faraday's law and Lenz's law. So this inductor tries to keep current flowing. And it's going to do that by inducing a negative V sub L, right? A negative V sub L will try to keep IL flowing to the right here. Okay, and the diode in this configuration will pass the current from left to right through itself. So it's passing current from the left-hand side to the right-hand side to the capacitor and the load. And so with that current coming in, that current through the diode charges the capacitor, right? That capacitor that was discharging on the left is now charging on the right. Current's flowing in. And that current also is supplied to the load. So you have the source and that stored energy in the inductor dissipating into the load and charging the capacitor. So let's look at the voltages here. If you look at the voltages, so if, again, run a KVL equation, you'll see that V load is equal to V source minus VL and minus VD. And it looks like, well, wait a minute. Load is going to be lower than source because I'm subtracting two voltage values here. But remember, VL is negative. VL is a negative value. That's what is happening here to keep IL flowing when that magnetic field is elapsing. So VL is negative, and VD is small. So really, you're adding a value here. You are subtracting this diode voltage, but that's usually small. If it's like a Schottky diode, it's 0.2, 0.3 volts, something like that. So V load is greater than V source, right? V source minus a negative value minus positive VD small gives you a load voltage that is larger than V source. Okay, so we've stepped up the voltage. Okay, and so let's see. Someone asks in the chat, would this only work for AC, alternating current? I thought current does not flow through a capacitor in DC. You're exactly right. So if I apply DC across a capacitor, current doesn't flow. DC doesn't flow across a capacitor. But think about when back to RC circuits, when you first connect a voltage through a resistor to a capacitor, that capacitor charges up, charge accumulates in that capacitor. So that means some current has to flow, right? Current is just the 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 flow of charge. So as you're charging a capacitor, current flows. Let's say you just attach DC to a capacitor through a little resistor. Um, the capacitor charges up, current flows. There's an exponential rise. You reach steady state. The capacitor is charged, and then no DC current flows. But for that short time when the capacitor is charging, you get this exponential. If you have a resistor and capacitor, you get an exponential rise, an exponential current that starts at some value and decays down to zero. So that's what's happening here. This isn't really DC. It's more like a square wave applied to that capacitor because you're opening and closing this. So this is going to happen. You're going to open and close this switch rapidly. And so this capacitor is charging up, right? So current's flowing, charging the capacitor. In the right case, here's where it's charging. And then on the left side, it's discharging. So that capacitor is constantly charging, discharging, charging, discharging. So that looks like an AC signal, right? And then on average, it's providing a voltage, a DC voltage to that load. Okay, so that's a good observation. So the duty cycle of the switch, right, of the control voltage that is controlling the switch, controls the load voltage. And because you're using on-off switching versus analog control, this makes this converter more efficient than a linear voltage regulator. So remember when we looked at two cases for a MOSFET, when you turn the MOSFET on and off, use pulse width modulation to create a voltage, or you just change the control voltage so you vary VDS to create a voltage, right? Switching on and off was more efficient. Okay, so and the linear voltage regulator actually has a finite non-zero voltage drop across it with current flowing through the regulator, right, through the pass element, and so that makes it less efficient for you know, especially for higher voltage differences between source and load. Okay, so that's the good news, but the bad news is on-off switching causes ripple and noise in the load voltage. So you can imagine you've got this capacitor discharging into the load, there's going to be some ripple voltage, right? That capacitor, just let's say the load is a resistor, it's probably not. Let's say it's a resistor. Either way, the voltage across the capacitor is going to drop a little bit as it discharges. And then it charges, and then it discharges, and so you get a little ripple voltage across the load. Okay. And again, that's where you might say, well, maybe I don't drop the output of the DC to DC converter all the way to the load voltage. Maybe I drop it to, a few tenths of a volt above the load voltage, and then I use a linear regulator. And we'll talk about that a little bit. Okay. Okay, so this is a boost converter. So we're stepping up the voltage. So here are a few different DC to DC converter topologies. So let's suppose you want to step down in voltage. Right, I won't go through all of the current paths, and I'll show you the reference for this where you can read more, but here's the input voltage source, here's the load, and so you can see the current paths here. So we're going to step down a voltage from Vn down to Vout. When switch 1 is closed, you're connecting the voltage source through the inductor, building a magnetic field, charging a capacitor through the load, right? And then when you open up the switch, you get current flowing, well, now from the capacitor through the diode. The inductor keeps current flowing. It tries to keep current flowing through the load, and this will step down the voltage. Stepping down the voltage, that's called a buck converter. A buck converter steps down voltage. A buck boost converter can do both. In this topology, you have an input and you have an output, and the output can be either higher or lower, depending upon how you're modulating that switch. So you can see the current flow right here, right? When the switch is open, when the switch is closed. When the switch is closed, you have current flow here. when the switch is closed. Um, you have this current flow. When the switch is open, you get the green current flow here. Okay, and the diode um, with the diode there. And so the catch here is this. This is called a buck boost converter, but it's an inverting converter. So if VN is like positive 5 volts, B out is going to be a negative voltage. Okay, so this is what this does for you. Creates a higher or lower magnitude voltage, but the output voltage here is negative. So you got to take that into consideration how you use that output voltage. Right? You might be able to connect it so you have a positive voltage and isolate this input from ground, and we can talk about that. But this is generally an inverting converter. There's a two-stage buck boost converter that looks like this, and uh, so it has a couple inductors and a couple capacitors, and this will actually step up or step down and not invert. Okay. And so you can see this, you can go back to these slides, you can check out this reference and read more about these. So each topology has its own function and has its own advantages and disadvantages. So you can see there's some of these converters have fewer components, lower complexity, some have higher complexity. This one I showed you inverts its voltage. You've got to deal with that. Some of these have certain resonances based on the L and the C values that you choose, and each has ripple currents and causing ripple voltages because, well, they're switching on and off, and you have a capacitor and an inductor that have voltages across them that are varying slightly. So the board that you're using in lab, this is here in the lower right, uses this integrated circuit. So you commonly actually don't go build these from scratch. You could, and there might be cases where you want to, but I would first go look for an integrated circuit that does what I need it to do and has an application note or a data sheet that gives me guidance on what values of capacitors and inductors to use. So this is the schematic of that board. So you can see in the middle here, it's just a block. So you don't see what's going on inside with maybe a MOSFET in there. But here is the DC input on the left. Here's the DC output across the load on the right. Okay, so let's see what you can see here. You can see here is an output inductor that you have to add externally. So that inductor is right here. This is that inductor on the board, right? You can see here's a diode, right? I think that's a diode right there. Gotta look close. I think that's a diode. So you have this diode, and you have a couple capacitors. So your input capacitor, let's see, this is the input side. It looks like you've got a large, fairly large, that might be 100 microfarad input capacitor here. And here's the output capacitor here. Right. And then you have a couple resistors that you can use to adjust the voltage. So there's probably an internal regulator here that you're using to adjust the voltage. Okay. So now you can see what's going on in lab. Other topologies and DC to DC conversion types exist. So there's something called a charge pump or switch capacitor, and there are variations of the buck and boost. And again, check out this reference, search the web, you'll see different topologies with different advantages and disadvantages. And you can just look for DC to DC converters from manufacturers and just use the integrated circuit, look at the data sheet for the performance and see if it matches what you need. Okay. All right, so that's linear regulators and switching converters. So let's work a clicker problem now. We haven't done that in a while. Let's talk about linear regulator power efficiency. Okay, let's go back to that linear regulator. Now, a DC to DC converter, right, not a linear regulator, typically has an efficiency that ranges from 75% to 98%. So I've 75% is probably low. In the 90s is, I would expect, more reasonable for a reasonable power DC to DC converter. But that converter, as we said, has higher noise compared to a linear regulator. So suppose you need a low noise supply voltage for an automotive application. So you're considering a linear regulator instead of a switching regulator. All right, maybe you have a radio receiver or you have an audio amplifier. You don't want any kind of noise through it, or you have some kind of sensor that you have to power and you can't have any noise on the power supply voltage. So let's suppose you have a 12-volt supply nominally, and the device requires 5 volts and 2 amps. So it's a 10-watt device, and it needs 5 volts. Okay, so the question is, what is the power efficiency of the voltage conversion? And it looks like this. So here's 12 volts from your car nominally. When your car is running, it's 13.8 volts roughly, 13.6 to 14.2 somewhere, but let's just use 12 volts here. Okay, so 12 volts at the input, 5 volts at the output, 2 amps delivered to the load. Here's the load over here. And notice I have 3 terminals on this voltage regulator, input, output, and what I'll call a ground here. Well, that voltage divider that you saw in the internal circuits, they're really low current usually compared to your load voltage. So this is the quiescent current. If it's low compared to the output current, let's just ignore it. We're gonna ignore this. For example, for this 7805 cheap, simple linear voltage regulator, the quiescent current's 6 milliamps. That's really small compared to 2 amps. All right. So what that means is you can assume you have roughly 2 amps going into the linear voltage regulator and 2 amps coming out. It's 2 amps minus 6 milliamps, which is almost 2 amps. So power efficiency is the power out divided by the power in. And power in is the power delivered to the regulator from the source. That's the power your battery is supplying. Power out is the power delivered to the load from the voltage regulator, right? And that's going to be less because, well, the linear voltage regulator gets warm, burns up some power. Okay, so the question is, let's see here, let me start clicker. What is the power efficiency approximately? All right, so remember power in, you can calculate that from the input current, input voltage. Power out, you can calculate from the voltage and current delivered to the load. All right, take another, I don't know, 20 seconds. Take a guess if you haven't answered already. Okay, so let's talk about this. Okay, so Pn is Vn times In, 2 amps roughly, times 12 volts. You're putting 24 watts into this circuit from the battery. P out is I out, V out, 2 amps times 5 volts. That's 10 watts delivered to the load. And so the power efficiency is P out over Pn, 10 over 24, that's 41.7%. So roughly 40% of the power you're taking from the battery is getting where you want it to. 60% roughly is heating up the voltage regulator and going to a place generally you don't want it to unless you're trying to create a heater. Okay. Um, so so that's not great, right? I guess for your car, it really wouldn't matter. You know, when your car is running, your alternator's running, it's charging the battery, you're using a little energy, using a little gas to power this, but it's not going to be a big deal. That linear voltage regulator is probably going to get hot. You got to heat sink it, but you know, who cares if it's connected to your car? Maybe. But if this is a 12-volt battery that you have out in the woods connected to a sensor sensing, you know, something, temperature sensor or water level sensor, something like that, you know, you may have limited life of that battery, limited solar power, so you might not want to burn up 60% of the power if you're converting from 12 volts from a 12-volt battery to a 5-volt load. Okay, so that's something to consider. Notice that when I in is approximately equal to I out, so I in and I out are about the same, that P out over P in is approximately V out over V in. Okay, so V in closer to V out is more efficient, right? Then eta is closer to 100%. And on the lower side, right, when you get V in too close to V out, then the regulator doesn't work. So linear regulators specify a dropout voltage, and that's the minimum V in minus V out. Okay. So, well, what do you do if you have a 12-volt battery and you want to efficiently operate a 5-volt load and you want a low noise supply for your load? Well, you can use this hybrid DC conversion approach, right? So you can get better efficiency and almost as low noise if you first use a switching converter to convert to a lower voltage, and then use a linear regulator for the final voltage reduction. Okay, so you could use to the left of the linear regulator, you could put a DC to DC converter there, and then step down a little bit to the final load voltage. And the noise is reduced by the regulator's power supply rejection ratio. There's different terms for this, but there is a spec on how much you look in a data sheet, how much the linear voltage regulator can reduce noise from input to output. All right, any questions on this example? Okay. Okay. So the last time I taught this class, I got a question about power inverters. So I wanted to talk about power inverters a little bit. So we talked about DC to DC converters, two approaches to convert DC. Um, Power inverters, often that's what we call them, are used to convert DC to AC. Okay, so DC to AC power conversion is useful for creating portable AC power. Power derived from a battery or AC power created from a solar panel or a solar plus battery system. So, you know, if you're out in the woods and you're camping and you have a 12-volt battery and a solar panel and you want to run your, you know, some device that's AC, you can use a power inverter. And there are various approaches to creating AC power from a DC source, right? We're not going to talk about all of them. I'm just going to talk about a general approach that this is how it's generally done. So you have this DC source on the left, and you want AC out on the right. You want a power outlet on the right. You want something to plug into here. So your DC source is the input to a MOSFET driver circuit. And so that could be a push-pull circuit that causes current to flow. It can be an H bridge that causes not only current to flow on and off, but also reverses polarity. So there's different approaches here. There are different ways to do this. But in the end, you get some kind of pulsed waveform, okay, or some kind of AC waveform. And that may not be at the voltage that you want, so you can use an AC transformer to step up that what is normally a lower voltage to a higher voltage, because you want, in North America, 120 volts AC 60 hertz, 120 volts RMS AC 60 hertz. And then at the output here, there's an output stage usually that is filtering to try to possibly smooth the waveform, and also sensing in a feedback loop to control this MOSFET switch. Right? So it's some kind of switching control or PWM controller. So right here, this pulsed waveform, and usually somewhere in the following stages, you'll see shapes like this. Some older converters just used a square wave. Okay, so they would use a square wave through transformer, filter it, and you'd get not a very nice sine wave looking waveform. And some loads, especially some, if you're trying to run measurement instruments remotely, some equipment doesn't like square waves. It wants to see more of a pure sine wave. And then there are modified sine waves. Some of the lower medium cost converters, inverters would do this. So you'd have something that looks like this. And sometimes you'll see modified sine waves that have 2 levels, and sometimes I've seen more levels, maybe 3 levels in there. And then you can have pure sine wave inverters that give you a nice looking waveform, safer for all equipment, okay, but they're more expensive. And sometimes this pulse waveform is PWM. So you can see here when you have narrow pulses, you have a low output voltage at the output, and then the duty cycle increases, the duty cycle decreases. And that's how the waveform is formed. Okay, but I won't go into the details of all these. There's lots of resources. You can look at different approaches, but that's generally how these work. All right. Okay, so in summary, here are some important points and takeaways on this power sources and control topics. We talked about batteries, right? Batteries are important to operate without a connection to primary power sources. So if you're not connected to a primary power source because there's none nearby, or if you need to have power when you have intermittent power goes out in your house, you can use a battery. So when selecting the battery type, consider, well, are you going to use a primary battery, one-time use, or a secondary rechargeable battery? And what kind of load voltage and current do you need? Right? Or what kind of voltage do you need into your power converter circuit? What kind of swap C do you have available? Size, weight, volume, and cost. Okay. So size, weight, and power and cost. How much power do you need? How much heat are you going to dissipate? You got to think about all of that. How efficient is your circuit? And then how much capacity do you need? Right? So what capacity do you need? What discharge rate do you need? What's the temperature of the environment you're operating in? We talked about lithium AA's versus alkaline AA's and how they handle different temperatures. What's the replacement interval, and can you tolerate cheaper batteries and a shorter replacement interval? And then for rechargeable batteries, how deep can you discharge the battery? If you have a regular lead acid battery, its life will be reduced compared to a deep discharge battery if you have deep discharges. So we talked about batteries. We talked about controlling power, common approaches to control high current. We talked about mechanical switches, relays, and MOSFETs. We concentrated on MOSFETs to enable electrical control of large currents. And we talked about the electrical parameters of this topic that affect mechanical design. Right? Remember, pulse width modulation, PWM, versus linear control. PWM is more efficient. We talked about choosing a gate voltage to reduce RDS on, so you get less power dissipated by the MOSFET. We talked about different mechanical considerations, like how do you cool that MOSFET with a heat sink or connecting it to a case or having forced air? What do you do? How do you mount this MOSFET? Do you mount it to the case so that you can use the case as a heat sink? Right? What's your battery size, weight, and volume for the corresponding power loss and power efficiency and power delivery to your intended load? So that affects swap C again. Okay, we talked about conversion, voltage conversion, to enable the load to operate from a higher or lower source voltage. We talked about linear regulators, and we just did an example on power efficiency there, but you get low noise. And switching converters, high efficiency, but higher noise. So you have to define how clean you need your power. And there are many additional topics we could talk about. I would love to, but we have to get on to other topics. But I would say with the knowledge that you have now, with the terminology and these concepts, I think it's worth self-study. I think it's worth taking a look at some of these topics like AC power, right? How is AC power stepped up and stepped down, and how do you use it? How do you use transformers to step up and step down AC powers, and then rectifiers to convert AC to DC, right? And then here's a sort of a separate topic. How about solid state relays? If you have maybe an environment, maybe a high vibration environment or a shock environment that can't handle a mechanical relay, can you use a solid state relay? So those are good topics. Okay. So we have a couple minutes left, but I don't want to jump into the next major topic um, just yet. So we're going to start a new topic during the next lecture. So let's close here. So in closing, homework 4 is due Friday. Don't forget about that. Check Canvas for all the due dates and due times of the upcoming assignments in the lab that we're going to do this week. If you'd like to stop by and chat, stick around on this session. I will hold office hours in just a few seconds. So if you join, I'll see you there. If not, I'll see you next time. Have a great night.